This lecture is about a classic paper by Lucas and Stokey in 1983. It's optimal taxation with state contingent debt. It's going to be an economy without capital. So we're going to jump in and describe the setup. And I'm going to be using a quant-econ lecture on this subject as the text. So first thing we're going to do is battle plan is we're going to describe a competitive equilibrium with distorting taxes. And there's going to be a bunch of competitive equilibria, and they're going to be indexed by tax systems and borrowing systems. And that's what I'm going to do for the main part of this lecture. In the following lecture, I'm going to give a recursive formulation of a Ramsey problem. So here's where we're going to go. The problem is really a classic one, going back to Ricardo and before, about how a government should pay for a war. And Lucas and Stokey wrote this paper in order to try to understand what Barrow was talking about in an earlier paper in 1979 JPE. And Barrow achieved some outcomes, some rather striking outcomes, or made some assertions about government taxes and debt that we're going to revisit in a future lecture. And Lucas and Stokey were trying to describe a more complete general equilibrium setup than Barrow had to understand the issues. So we'll come back to that a little bit later. So let's jump into the Lucas and Stokey model. So the model is going to feature a government that just has an exogenous stream of government expenditures, and it has to finance them. It's not a model of optimal government expenditures. It's just some government expenditures that have to be financed. And it finances them in two ways. And these are ways that Lucas and Stokey forced the government to finance them. The first is a flat rate tax on labor. It's a distorting tax on labor. And the second is trading securities, aero securities, and there's going to be a full array of aero securities. And we're going to go back and forth between aero securities and aero debris securities. So there's going to be, in addition to the government, there's going to be a representative agent who cares about two things, consumption and leisure. It's going to be a standard sort of macro specification of this representative consumer. There's going to be a linear production function that maps labor into a single good. There's going to only be a single good. And there's going to be a government or a Ramsey planner who at time t equals 0, he's going to choose a plan for taxes and trades of aero securities for all time. So this is going to be a once and for all choice. In other words, he's going to be committed to it. So we're going to do this, formulate this problem in two different ways. First, we'll follow Lucas and Stokey and formulate the model in a space of sequences. And then after that, in our next lecture, we'll formulate it as a dynamic programming squared problem. So that's where we're going. Okay, so let's get some boilerplate notation, and this is going to be very much like chapter 8 of recursive macro theory. There's going to be a state ST, a Markov state. Well, we'll eventually make it Markov, but we'll only do that a little bit later. So there's going to be a history ST of an exogenous state, and before we make it Markov, we'll we'll just let there be a joint density over these histories. So pi t of S superscript t is going to be a joint density over the partial history up to date t. We're going to begin by assuming government purchases are history dependent, and they depend on the history. And as in chapter 8 of the book with Lundquist, we're going to let consumption, leisure, and labor all be potentially functions of the history. There'll be a sequence of functions of the histories. We're going to have a representative agent who's endowed with one unit of time, and he divides it between leisure and work. So that's going to be our technology following Lucas and Stokey. So output is going to be equal to the amount of labor that's supplied, and it can be divided. The feasibility constraint is it can be divided between consumption and exogenous government expenditures. So government expenditures are going to have to be essentially come out of total output. There's going to be a representative agent. It's going to maximize expected utility. And that's going to be this particular sum from, it's going to be infinite horizon. It's going to be discounted by this factor and by those probabilities. Consumption is going to depend on, utility is going to depend on consumption and leisure. The household likes both consumption and leisure. We'll make some assumptions about the differentiability of the utility function. So in this setting, it's easy to anticipate that a pre-tax wage is going to be equal to unity for all t. Technology is going to do that. So what the government's going to do is it's going to impose a flat rate tax on labor income, and the tax can depend on time and the history. So there's going to be a sequence of flat rate taxes that the government's going to choose at time zero. At t0, it's going to choose these whole things. And again, we're going to assume complete markets, as Lucas and Stokey did. In a subsequent setup, to get closer to Barrow, we're going to shut down complete markets, but not here. So there's going to be arrow securities, and with prices PT, I'm going to write it like this: of given this history, S superscript T, the price of 1 unit of consumption in state ST plus 1 is going to be PT, ST plus 1 condition on ST. And the government's going to issue, I could say, or buy 1 period error securities each period. Okay. So the government has a sequence of budget constraints. If we do it arrow style, we'll do this a couple ways. If it does it arrow style, the government's budget constraint is government expenditures have to be financed either by current tax revenues, and there's a flat rate tax times the amount of labor that's actually supplied. And that's one way to raise the revenues. The other way to raise revenues is to is to sell Aero securities in these amounts, state by state. The total amount of revenue raised is going to be this sum. And then, of course, the government is going to have to repay the state contingent securities that it contracted to if state ST appears. So this is that's the budget constraint. Okay, and we're going to start off, and this is going to be important, we're going to start off initial government debt that the government owes is going to be B0 of S0. We're going to take that as an initial condition. And this is going to be important down the line. Okay, so watch for the appearance of this term. Okay, so the representative agent is going to have a sequence of all Raw's laws in play. It's going to have a sequence of budget constraint with the time t component looking like this. On the left-hand side, what does the agent spend? He spends consumption. He buys the Aero securities issued by the government. Okay, his revenues are his after-tax wage payments and the income that he gets from the Aero securities that paid off this period. Okay, so then we use some of the standard definitions. What's a government policy? Well, it's going to be this exogenous sequence of government expenditures. It's going to be a tax rate sequence. And it's going to be a government debt sequence. That's what we mean by a government policy, all those things. Some people would call that a fiscal policy. We're going to have a definition of a feasible allocation. It's a consumption labor supply that satisfies our feasibility condition for all t. We're going to have a price system. Our equilibrium notion is the household is going to face the price system as a price taker, and it's going to take government policy as given. So it faces two things. It faces a price system and it faces a government policy. And what's the household going to do? It's a standard thing in any competitive equilibrium. It's going to choose consumption and labor supply to maximize expected utility, subject to its budget constraint and subject to this technological, this feasibility technological constraint. Okay, so then we define a competitive equilibrium of distorting taxes in a standard way. It's a feasible allocation, it's a price system, and it's a government policy such that given the price system and the policy, the government policy, the allocation solves the household's problem, and given the allocation, government policy and the price system, the government's budget constraints satisfied. So this is the extra piece that the government's presence puts on a competitive equilibrium. So here's the key thing. There's a huge number of competitive equilibrium with distorted taxes, and these equilibria are indexed by different government policies. There's not a unique competitive equilibrium, and that's an important ingredient of the Lucas-Stokey problem. So what the Ramsey problem is, also called the optimal taxation problem, it's to choose a competitive equilibrium with distorting taxes that maximizes expected utility of the representative household. Remember what 3 is. So it's to choose the best. It's to choose the best competitive equilibrium, where best means maximize this. Okay. Now that's different from this is not the Pareto problem. where it's not a planning problem. Because in addition to the restrictions from feasibility, in addition to those restrictions, we have to restrict the allocation to be a competitive equilibrium with distorting taxes. And the pure planning problem that we talked about in chapter 8 of RMT would be it would not have this piece. Okay. So to solve this problem, we're going to find it convenient to basically follow Lucas-Stokey, and we're going to work with an Arrow-Debreu version of the price system. Okay, so there's an equivalence, Arrow showed this, between equilibria supported by Arrow securities prices and Arrow-Debreu prices. So we're going to let QT0 as a function of the history of ST be the price at time zero, measured in time zero consumption goods of 1 unit of consumption at time t history ST. So this is going to be an Arrow-Debreu price. And from chapter 8 of RMT4, we recall this nice recursion that links Arrow-Debreu prices and Arrow securities prices. And this looks a lot like an analogous relationship that exists between joint densities and conditional densities for in probability theory. And we're going to use these when we want to express a sequence of budget constraints. We want to summarize them in terms of a single restriction on the entire sequence. We'll come back to this. So another thing we're going to use in this, that Lucas and Stokey uses, they use the so-called primal approach. And this is based on a prayer and a hope. The hope is that the first order conditions of the household sector are sufficient to summarize their optimum decisions. And this is something that may or may not be true, and there are counterexamples, but Lucas and Stokey are relying on it being true. And for problems with sufficiently small government expenditure processes, there's an argument that can be made that it is true. But we're not going to verify that in this lecture. Okay, so here's going to be the strategy. It's going to consist of these steps. This is straight out of Lucas and Stokey. First thing we're going to do is we're going to obtain the household's first order conditions, and we're going to stare at them, and we're going to use them to express prices and taxes as functions of the allocation. We're going to get the first order conditions, and we're going to find prices and taxes as functions of real things. And then we're going to take those functions and we're going to substitute them in to the household's or the government's present value budget constraint. And then we're going to note that this intertemporal constraint only involves the allocation. So no prices and no taxes. They've been substituted out. They're in there only implicitly. And we're going to regard that single intertemporal constraint as a so-called implementability constraint. It's going to be an additional constraint beyond feasibility on the planner, on the Ramsey planner. This is going to be. Okay. So then after we do that, we're going to find the allocation that maximizes the utility of the representative consumer, subject to the feasibility constraints and the implementability constraint we just derived. And the application that solves this problem is called the Ramsey allocation. And then once we're done finding the allocation, we're going to return to the formulas that we found in step 1 that express taxes and prices as functions of the allocation. And we're going to back out the taxes and the prices. That's the program. So again, these 4 steps, get the first order conditions. That's why this is called a first order approach. Solve those first order conditions for prices and taxes as functions of the allocations. And then temporarily forget about the taxes and the prices and work only in terms of allocations in steps 2 and 3. And then only at step 4 do we come back and recover the taxes and prices. So let's do it. Following Lucas and Stokey. So first thing we're going to do is we're going to write the summarize the sequence of government budget constraints that we had before when we wrote these things, arrow security style. We're going to write those in terms of arrow de Brue prices. So what do we get? When we do that, this looks like a version of stuff we did repeatedly in chapter 8 last year with Lars Lindquist. The left-hand side is the present value of consumption. On the right-hand side, this is the present value of after-tax labor income. And then what this is the initial government debt that the household owns. This term is going to play a role in especially when we come to discuss the time consistency or inconsistency of the Ramsey plan. So this was the initial government debt. Okay, that's the budget constraint of the household. So now what we're going to do is we're going to do step 1. We're going to get the first order conditions of the household. And when we do that, we get this condition. That's the atemporal optimum condition, which says that the 1 minus the tax rate is equal to the ratio of the marginal utility of leisure to the marginal utility of consumption. And the second condition is that the arrow security price is equal to beta times this conditional probability times the ratio of marginal utilities of consumption next period and this period. So this condition will be familiar from chapter 8. So those are those 2 first order conditions, and they're going to do the job for us. We're going to use this to solve for taxes, and we're going to use this to solve for this arrow security price. And it follows immediately that if we know the arrow security price, we can use that recursion that we have earlier, and we can get the arrow de Brue price only in terms of the allocation. So this is a function of C and L or N, as is this. So what we're going to do is we're going to substitute from those 2 first order conditions, and we're going to substitute into the household's budget constraint those 2 conditions to arrive at this equation. So this piece we got from the Arrow de Brew prices as this piece. So what we've actually multiplied through by UCS0. So this is the so-called implementability condition. It involves only the allocation. So stare at that for a while. So I recommend pausing the lecture and staring at this for a while, as also in the note. And notice what's going to play a role in a little bit is if initial government debt is 0, this term would not be there. So starting out the system with B0 equals 0 is going to have consequences. In general, it's not 0. Okay, so the Ramsey problem is to choose a feasible allocation, and feasibility means that CT plus GT is equal to NT for all T for all ST. That's what feasibility means. So the Ramsey problem is to choose a feasible allocation that maximizes the utility functional of the representative consumer, subject to this implementability condition. Okay. And that implementability condition says that the allocation that's being chosen has to be one that is associated with a competitive equilibrium with distorting taxes. That's what it means. So how are we going to solve this? Well, we'll follow Lucas-Stokey, and we'll put a Lagrange multiplier, big phi. So there's going to be one implementability condition. One and only one. This is a telltale sign of this Lucas-Stokey complete markets model. We put a Lagrange multiplier on that, and then we're going to formulate a Lagrangian and get the first order conditions, stare, and solve. That's our whole program. So to do this, we can get some insights by defining this thing that we can think of a pseudo utility function. We'll call it U of V, we'll call it V of CT, NT, and that's work, and we have to put a Lagrange multiplier in there. So that's just our utility, one period utility function, and we're going to add phi times this piece right here. And what is that piece? That's this piece here. So if we just mechanically, this is just mechanics. We can then form the Lagrangian. I call it a pseudo utility function because now I'm just going to treat this as an ordinary chapter 8 planning problem with a funny utility function. Instead of U here, I'm going to have this phi. So conditional on phi, this thing looks just like a chapter 8 problem, with one exception. There's this special term at the end when I formulate this Lagrangian. I picked up that term when I wrote the Lagrangian. Now, that term would be out of there if B0 were 0, but in general it's there. So now, what I've done is I've added fees. This is my feasibility. I've absorbed the implementability condition into this funny v function and this term at the end. Okay, so now what am I going to do is I'm going to use standard Lagrange multiplier theory for a given phi, which I'll worry about later, and a given initial debt. I want to maximize J, this Lagrangian, with respect to the allocation, and I want to minimize it with respect to these Lagrange multipliers on the feasibility constraint. That's my problem. Okay. So here we go. So we're going to now get the first order conditions. And what we're going to do, we get these first order conditions, we're going to be careful. So I urge you to go through these things. We're going to distinguish the first order conditions for periods t greater than or equal to 1 and t equal to 0. And the reason that we're going to have to do that is that the t equals 0 term looks different. Why? Because N0 and C0 influence the marginal utility of consumption at time 0, and it appears here. And it also appears here. But this term only appears only at equal to T0. There's no such term. There's no such term in here. That's just that's just a comment when you're doing the differentiation. Okay. So when we do this, we get first order conditions, set of first order conditions for t greater than or equal to 1. That's the first order condition with respect to consumption. That's the first order condition with respect to labor. We've substituted out leisure for labor. And for t equals 0, we get we get marginal conditions that look almost the same, except for, I'll be fancy here with color, almost the same, except for the additional presence of these terms right here. And those were the terms that were inherited from this business up here. Okay. So the first, we've completed now, having derived 15 and 16, we've completed the first step of our recipe. In doing the first order conditions. So now what we're going to do is, to start this, to get some insights, we can eliminate, we can attack number 15, and we can eliminate these multipliers. Essentially, how are we going to do it? We're just going to add up, if we just add up these first two equations, we add them up and rearrange, we get this single equation, 17. And now I'm going to stare at this, because we can get the principal insights of 80% of what Lucas and Stokey talk about in their paper from this single equation. Now, this only applies for t greater or equal to 1. So remember that. Well, if we look at this equation, this is, it's kind of remarkable because, so now what I've done is I've suppressed the time and subscript and the index st, but every place you see a c or a g, you should understand that that is also a function of t st. But if you look at this, this itself, this equation, this is a static equation, meaning it's one equation. It's one equation that can be used to, it can be used to express c, which is endogenous, as a function of g. So we can solve this as for c as a function of g alone. And then we can use feasibility to solve for n as a function of g. And which g is it? It's only the current g. So some magic has happened here because we allowed, notice what we did. We allowed g to be history dependent. We allowed consumption and labor supply and taxes all to be history contingent. But what we found as a result of our analysis is that the optimum, in the Ramsey plan, the optimum choice is going to make c and n only a function of the current g. Only a function of the current g. And again, government debt does not appear as an independent variable in this equation 17. So there's no government debt here. So you could ask, how could government debt possibly appear indirectly in this equation? Well, there's only one way, and it's through phi. Only the occurrence of phi here can something about government debt, in particular the initial value of government debt. So B0, whether you're from a high debt country, B0 can influence C, T, NT for t greater or equal to 1 only through phi, which we have temporarily taken as given. That's what this mechanics is indicating to us. Okay. So if we go through the same logic, and we apply this to do the same logic that we did here for 17, and we apply it for these equations 16, what we find, this is important, is we're going to get C0 and N0. They're going to be functions of G0, of S0, and B0, as well as of phi. So and in particular, they're going to be different functions than for t greater or equal to 1. So there's a different function for consumption and labor at time 0, and for all t's greater or equal to 1. And this is going to be a telltale indication of time inconsistency of the Ramsey plan. So getting back to this, earlier insight, so for any two histories, for t greater than or equal to 1, for any two histories that lead to the same g, we get exactly the same choices of consumption and leisure, or consumption and employment. So this is a version of something we saw similar to a result in RMT Chapter 8. I'll let you think about that. This is just another way of reasserting that for t greater than or equal to 1, the history by which you got to this particular g, value of g at time t, is irrelevant. You would do the same, the Ramsey planner would choose the same consumption and the same employment for those two histories. Okay. So the Ramsey allocation for a given fee, so we're ready kind of to unwind this. Well, this is all summary. So how do we choose fee? What we have to do, at the end of the day, we have to adjust fee after we've done this. So once we've got down to here, is we've taken fee as given. For a given fee, we've solved for C0, G0, and we've solved for CT, GT for all t greater than or equal to 1. And now we have to check if the government budget constraint, the consumer or government budget constraint is satisfied. It may not be. And if it isn't, we have to adjust fee. So we move fee up or down. So that's what we're going to do. We're going to illustrate this with the by specializing the problem a little bit, and we're going to specialize a la Lucas and Stokey. They assume Markov from the beginning. So above, we did not assume Markov S, but here we're going to assume a Markov S. So we're going to assume that S is now governed by a finite Markov chain. You'll see we're kind of mimicking the structure of Chapter 8. And we're going to assume that government expenditures are an exact function of the Markov state. And now we're going to show you how to solve for phi in this context. And later we'll write a Python program that does this, but you'll see how to do it. So now here we go. Again, this is repetition. First order conditions are going to be that for taxes. Our error security prices are this. But now I'm going to write I'm going to write a recursive version of the household budget constraint, taking account of my Markov structure. And if I do this, I'm going to get big dividends from Markov process right away. I'm now going to, this is arrow security star, or a recursive version of the arrow de Bruce budget constraint. I would get this equation. Now I'm going to stare at this, and I'm going to look at this here and this here. And if I do that, I'm tempted to call this xt, and this xt plus 1. Of course, this is going to be a function of st plus 1, and this is going to be a function of st. I'm going to define that. In which case, this thing looks like an asset pricing equation. It's a very simple asset pricing equation, which I'm tempted to solve. See, this term now is just the beta times the expected value of x next period. And this is just a bunch of stuff at time t. So this looks like a kind of equation that Schiller made a lot of insights from. So this means I can write this equation like this. This is expressing x as a, pull this to the other side, as something depending on, this expresses x today as a function of some stuff that depends on the Markov state today, plus beta times the expected value of s next period. And I can rearrange that into vectors, and I can use this, in chapter 8 we called I minus beta pi, we call that a resolvent matrix, or a resolvent operator. I just get this is just a standard application of an asset pricing equation. So I can solve directly for x as a function of the other objects, consumption and labor and leisure, and those margin utilities. Okay. So now after solving for x, I can easily find b. Just using this matrix equation. I have that. And so now I have my computational algorithm for solving for phi. I'm going to make a guess of phi. I'm going to use the first order conditions and the feasibility conditions to compute my consumption and labor. And I'm going to compute this. And if I count equations, these are this is a system of equations of s plus 1 2 times s plus 1 equations and 2s plus 1 unknowns. I can solve them. I'm then now going to solve for the x's. Those depend on phi. And now I'm just going to iterate and solve. I'm going to search for a phi that solves this equation. And I'm going to just do it by, I'm going to check if 25 is satisfied. If it's not, I'm going to adjust phi to make it satisfied, using something like a Fibonacci or some kind of search algorithm. And then finally, after computing the Ramsey allocation, I'm going to back out the taxes. I'm going to back out the arrow security prices. And so at the end of the day, here's the punchline. When things are Markov, finite state, I can solve for a Ramsey plan, by solving a finite set of equations. And I'll let you spend some time on this. Okay, so let's just wrap this up by a couple comments about time and consistency. So we'll define a Ramsey plan as we have before. It's a sequence of taxes and an associated government borrowing strategy from time t equals 0 on for infinity. And in this setting, it's going to be this. Everything's going to be history dependent in general. And then we're going to define a continuation. We're going to define a continuation of a Ramsey plan as just being the natural thing. It's going to be the same thing, but it's going to start from a history at some later date. Okay. It's going to be the tail of the Ramsey plan starting from date t. So the key thing is a time t, this is the key thing, a time t history st continuation of a time 0, state 0 Ramsey plan is not a time t history st Ramsey plan. And the reason is, again, the first order conditions. When you stare at the original first order conditions, and this is going to have to do with the presence or absence of this term in the first order conditions. So I'm going to stop here. We've set the stage for a discussion of time inconsistency that we're going to attempt to clarify by applying our dynamic programming squared approach to this problem. We're going to try to Bellmanize this Ramsey plan, and a key thing we're going to use to Bellmanize it is essentially noticing the structure of this equation and the role of x here.